This project is about developing an app to focus the parking demand in San Francisco. For big cities like San Francisco, there are always parking issues. Drivers cannot find the parking spaces during the busy hour, and there's always need to rebalance the parking occupancy. There might be some related issues like traffic congestion and environment pollution. The app is trying to solve these problems. Our target users are people who are looking for parking spaces. They can know about the price and occupancy of their destination at the arrival time before actually going there. This encourages them to park in the streets and blocks which are not busy. Our goals are not only providing help for drivers. We also hope this app can help forming an auto rebalance system. In the background research, we know that policies like dynamic pricing always have a lag effect on parking behavior several weeks later than the change of the price. But with our app, drivers will be noticed of the occupancy and the price information in time, so they will adjust their parking behaviors automatically. This will also increase the effects of pricing policy. This is our user interface. Drivers can just simply input their destination, and the app will calculate the arrival time and showing the occupancy and the price. If there is high occupancy at the destination, the app will also recommend some other streets around to park, and showing the details of this street for the drivers to choose. Then, how we are going to realize that? First, we download the 2 weeks parking data of San Francisco. We found that most of the parking behavior start after 9 a.m. and end before 6 p.m. That will be our study period. We developed an algorithm called time token to calculate the occupancy of each time. We round every parking behavior into 15 minutes intervals. We calculate time tokens based on how long a parking behavior lasts. For example, 1 hour parking will get you 4 tokens. As parking continues to next few time periods, the time tokens also goes to next few rows. By adding all the tokens in each row, we get how many tokens at each time period. We divide the parking daytime into 3 time periods. We assume that for parking behavior start from 9 to 12, the max parking time is 9 hours, because they will end before 6 p.m. And the same for parking behavior start from 12 to 15, 15 to 18. Now we get all the tokens for each meter at each time. Then we will sum tokens for all the meters in a street and divide by all the parking spaces of this street. That's our occupancy. With the occupancy, we can do more data exploration to find the predictors. We found out that other than Sunday, when the meter is not charging, the other days of week have effects on the occupancy, but not much. We also explore the relationship between parking price and occupancy. It seems that there's no obvious linear relationship between them. However, remember the parking rate has a lag effect on the parking behavior, so we will also include the parking rates 2 weeks before as the predictor. We will use linear regression model. The dependent variable is the parking occupancy. The predictors is the demographic features, urban facilities, spatial time lag, and also the price we mentioned before. The demographic features comes from census data, and urban facilities data came from OpenStreetMap. We will use k-nearest neighbor and buffers to calculate them. Last, we will also include the spatial lag, which is the occupancy of the nearby street, and the time lag, which is the occupancy 1 hour before, 3 hours before, 6 hours before, and 1 day before. We randomly divide our data, 70% of them as training set, and 30% as testing set. We use the model trained by training set to predict the results of testing set. Finally, we got a 0.03 MAE, which means the model is pretty good. We can also see that in the plot of a comparison of the predicted occupancy and the actual occupancy in testing set. We strongly recommend this model in actual use, which we believe will solve a lot of parking issues in San Francisco.